To all of you joining me for this video, I am Mr. Ish. Thank you for joining me. For a set of curves which undergoes dynamic rotational movement, we have y equals x cubed, we have y equals root x, about x equals minus 2, which you know is a vertical line of axis or vertical line of rotation. When you're looking at this, it's not too hard. Just think about y equals x cubed as something which would look something like that, and you know it would come down over here like a cubic function. My curve here looks a bit exaggerated, but ignore that. Y equals root x would look something like this. The region between these two is the area which would be rotated around your particular line of axis, x equals minus 2, which would be right over here. And then you would rotate it around that. Remember, vertical line of axis requires everything to be presented in a particular way. What is that particular way? Your equations have to be converted into x equals format. If y is equal to x cubed, then x is equal to cube root of y, which is, well, you can just say y to the 1 over 3. If y is equal to root x, then x is equal to y squared. Those are your two forms. Everything will be done here for the volume determination with respect to dy, not dx but dy, because again, vertical line of axis. This stuff that I'm telling you applies to this type of question when you're doing the disc and the washer technique, not if you're doing the cylindrical shells. Anyhow, we're going to do a disc and washer method, and that's exactly what we're looking at. When you're doing something around this, what will your representation be with regards to a solid? Well, it would come on this side as something like this and something like this. Here's your line of rotation. Then you know you're going to do a rotation and you develop this solid. When you develop the solid, it will look something like this. Of course, it's a very rough representation only, but that's exactly what it looked like. It looked like a bowl, except the bowl will have a convexity on the inner and the outer aspect, a convexity which will be circumferentially found all around. But if you were to pluck out a section from here, when you pluck it out, you would have a washer, and that exactly right here would represent your x equals minus 2 line from here to this first edge, and then here from your center to the first edge, center to the outer edge, you have your inner radii and you have your outer radii, which will give rise to inner area and outer area. But how do you bring all of that into perspective for this? I'll show you. I'll erase this because you don't need to see the solid. You can picture it in your mind, but that's exactly what we're looking at. When you're looking here from your x equals minus 2, you are going to go across to your first curve. That first curve will represent your inner radius. From that same line of axis, you go to the next curve, that'll be your outer radius. What's your inner radius? What's your outer radius? Well, if you're looking here, everything from x equals minus 2, in terms of distance, which is always positive, you're looking here from 2 plus, because you're already 2 units away from this y-axis, after which you judge the distance to your curve. 2 plus this curve right here, which is your root x, but that's really y squared. And then outer radius. You're 2 units away to the y-axis, but then you're a certain number of units away to this curve, which is x cubed, but now it's really y to the 1 over 3. 2 plus y to the 1 over 3. Now this right here will have to go through the area formula for circles, because everything here is circular. When you're looking here at area of the inner, you're looking here at 2 plus y square, whole square, and pi. Pi r square. That's exactly what you have. When you're looking here at the outer area, what are you going to have? You'll have 2 plus y to the 1 over 3 whole square, pi r square in both instances. When you're doing your volume determination, you're looking here with the pi's pushed outside, but you're looking from a lower limit, upper limit. Now, are you going to look along the x-axis or the y-axis? Well, when you do with regards to dy, you're looking here along the y-axis. What will your points be? Well, you know you have one intersection here, 0 at the origin. What's this intersection point right here? Because that's going to translate to your upper limit. That will be equal to both of these. You will have x cubed is equal to root x. X cubed minus root x is equal to 0. You can isolate an x to the 1 over 2. And then you'll have x here, 5 over 2 minus 1 equals 0. When you open up all of this, you'll have everything here. Then x is equal to 0 and 1. So your one intersection point is 0 in terms of x. When you put 0 in any of these equations, you get 0, 0. So that's your y value. When you put 1 in any of these equations, you get your 1, 1. And that's exactly how you're determining your upper and your lower limits. And you're going to do outer area minus inner area with respect to dy. Now we've established everything. Now we have the work part. The work part is just the integration this definite integration, but it'll be polynomials all the way through. We'll have a bit of work when we open this up, so let's do it. We'll have pi 0 to 1. We'll open this outer area minus inner area. You'll have 4 plus y to the 2 over 3. Remember, it's a plus b whole square, which is a square plus 2ab plus b square, plus 4y to the 1 over 3 minus, we'll do this part right here, which will be 4 plus y to the 4. Again, this is a plus b whole square plus 4y square, all with respect to dy. When you open this up, we have to open it up actually. You'll have pi, and then you'll have all of these items come through. You'll have y to the 2 over 3 plus 4y to the 1 over 3 minus y to the 4 minus 4y square dy. And this right here is polynomial integration. Y to the 2 over 3, remember it's n plus 1 divided by n plus 1. It'll be y to the 5 over 3 over 5 over 3. Here you'll have 4 y to the 4 over 3 over 4 over 3 minus, here you'll have y to the 5 over 5. Here you'll have minus 4y cube over 3. Everything here from 1 and 0. Now, within the same location over here, I'm going to start adjusting these denominators. I have a 5 over 3. It'll become 3 over 5. I have a 4 over 3. I'll multiply with this. It'll become 12 over 4. 4 divided by 4 over 3 is a 12 over 4, which is a 3. We can eliminate this denominator line. We don't need it. Then we have all of that. Now, when you're putting in 1 and a 0 as the upper and the lower limits respectively, the 0 is meaningless but the 1 is not. You're essentially just looking at 3 over 5 plus 3 minus 1 over 5 minus 4 over 3. And I want to do all of that right over here on the left side. I'll erase this because you don't need to see this part here. I really have a pi. And then I have a 3 over 5 plus 3 minus 1 over 5 minus 4 over 3. That's exactly what I have. And the common denominators, 5 and a 3, are just 15. I'll have a pi sitting outside. 5 goes in 15 3 times. 3 times 3 is a 9. Plus 1 goes in 15 times 3 is a 45. Minus 5 goes in 15 3 times that 1 is a 3. And then lastly, 3 goes in 15 5 times that 4 is a 20 minus 20. You just have to add all of that up and you get your final answer. We'll do 9 plus 45 minus 3 minus 20. We have 31 pi over 15, and that'll be our answer. Volume with respect to y here is 31 pi over 15, and that will be our answer, and it should be right. Let me just improve my writing over there. 31 pi over 15 will represent the volume of this solid as it rotates around this. Now, is this solid revolutionary solid or rotational solid? Well, as you saw it looked like that bowl revolving around this x equals minus 2, because this specific point here does not stay put as everything else moves. In this particular case, everything is undergoing this circulatory translational movement, so we really have a revolutionary solid, a solid of revolution, not truly a solid of rotation, though generally it is everything I'm saying, but truly it is a solid of revolution because everything is undergoing translatory movement around a circular path over and about this line of axis. And that's it for this particular video. Everything should be right over here as presented. Outer area minus inner area over vertical lines of limits, everything with respect to dy, because we have a movement here along a vertical line of axis. Equations are in the x equals format. And lastly, let's not forget the particular fact, here we utilize the washer method of integration. Thank you for watching. Have a good day. Bye.